Hello and welcome. In this video, we're going to take a look at a couple theorems, and they really involve a lot of what we've learned about with continuity and derivatives. So one of them is called Rolle's theorem, and the other is the mean value theorem. They're very similar. In fact, you could think about the mean value theorem as being like a generalization of Rolle's theorem. So let's start off with Rolle's theorem, see what that gives us, what it can be used for, and then take a look at the mean value theorem. Now, starting off with Rolle's theorem, we let f be a function that satisfies three criteria. It needs to satisfy all three of these for the conclusion to be guaranteed. That's the idea of a theorem. So long as the three boxes are checked, we know that the conclusion is always true. So the first thing is this function needs to be continuous from the closed endpoints a to b. So it can be continuous just from one side at A and B. It needs to be continuous the whole way through. No asymptotes, no jump discontinuities, no removable discontinuities. Just a very nice function. F also needs to be differentiable on the open interval from A to B, not including the endpoints. The function needs to be, smooth. It can't have a sharp corner, and it can't have a vertical tangent line anywhere. Last but not least, third criteria, f of a needs to equal f of b. That just means that at the endpoints, the function evaluates the same number. So really think about on the y-axis, it starts and ends at the same coordinate on the y-axis. If those three things hold, then the function is guaranteed to have some number between a and b where the derivative at that value equals 0. So it has a horizontal tangent. So I could try maybe turning this language into a picture, and that might help to illustrate this. Right. Well, we'll start off with drawing a function that satisfies the three criteria. It might be easiest to at least include that interval along the x-axis from a to b. And let's start off with that third criteria. F of a needs to equal f of b. So wherever you want to put your first endpoint, their second endpoint needs to be exactly at that same height. F of a equals f of b is criteria number 3. And that's a value on the y-axis. Now, the other two criteria are just kind of indicating the behavior of this function. And because it's a function, it has to pass the vertical line test. Because it's continuous, it can't have any breaks, any removable discontinuities. Because it's differentiable, it can't have sharp corners or vertical tangent lines. It really restricts how you draw your function. We have to go from one point to the next. You can be relatively creative with going up and down, but you can't be anything sharp corners and you can't have any discontinuities. And you'll notice that as I do that, there's going to be places where my function needs to have tangent lines that are horizontal. That means that there exists some number between a and b where the derivative at that number equals 0. So one of the numbers here that would satisfy Rolle's theorem would be this number c. There's also another place here, we could call this c1 and c2. There's actually two different numbers, two different values that satisfy Rolle's theorem. There has to be a number, at least one, that satisfies Rolle's theorem if the three conditions hold. The moment that we have a function that is not continuous or not differentiable, that does not guarantee the existence of some horizontal tangent line in the interval. Now, similar to that, we also have the mean value theorem. Now, the mean value theorem is very similar, but requires only two criteria on the function. It needs to be continuous on the closed interval, including endpoints from a to b, and differentiable on the open interval, not including endpoints from a to b. This time around, we say that if a function satisfies both of those criteria, it's guaranteed that there is some value c that exists in the interval between a and b, such that f prime of c equals this number, f of b minus f of a over b minus a. And you might recognize that as being y2 minus y1 over x2 minus x1, which is the slope of a secant line. It's the slope of a line connecting the function at x equals a and x equals b. Again, this really works a lot better if we try to illustrate this. Now this time around, the third criteria of Rolle's theorem has been removed. That's why we can really think about the mean value theorem as being more of a generalized theorem. From A to B, we have our interval, and this time around, f of A does not have to equal f of B. We can place them wherever we like. Here's one endpoint, and that would be at a value f of A, and that would be along the y-axis. And let's say f of B is a different number. So we can put the other endpoint further up here, and f of B is higher on the y-axis. Now, make sure that you draw a function connecting those 2 points that is passing the vertical line test, it is continuous, and is differentiable. I'm not going to be overly creative here. I could just simply make this a nice arc. But you could also have a much more interesting polynomial, up and down, or any kind of behavior you wish, so long as it satisfies the criteria. Well, now that we've drawn the curve here, we can see that this f of b minus f of a over b minus a, well, that's the slope of a secant line connecting the 2 endpoints. So if we were to try to make a nice smooth line here, connecting the endpoints, then the slope of this line is f of b minus f of a over b minus a. And if we have a function that's continuous and differentiable, then there's some value c where the derivative at c is that same value. So that's just saying that there would be some point on this curve where the tangent would have exactly the same slope. So you can see there would be a point roughly around here, and that would be a value c that satisfies the mean value theorem. F prime of c would be this slope, and they are exactly parallel, so they have the same slope. That's what the mean value theorem is saying. And you can imagine that is really just a generalized version of Rolle's theorem, because really the difference in Rolle's theorem is that f of a and f of b must be the same. If we were to connect the endpoints, it would be a slope of 0, and then we'd have to have a tangent slope somewhere with 0. Mean value doesn't have that restriction. Now, where are these two theorems useful? Let's start with Rolle's theorem. What kind of situation would we use Rolle's theorem in? In this example, let's see if we can show that 2x cubed plus 3x minus 6 equals 0 has only one solution. And maybe a better way to think about that is to let this be a function, f of x equals 2x cubed plus 3x minus 6, and show that it crosses the x-axis at only one place. And we can start off by looking at the intermediate value theorem to show that the function must cross the x-axis. For that, we have to at least state that this function is continuous over some interval, and at one endpoint it needs to be below the x-axis, and at one endpoint it needs to be above the x-axis. Now, of course, this function is continuous over the whole real numbers because it's a polynomial, so we can pick any interval that we like. Now, we want at least one endpoint where this function is negative, and it's pretty easy to plug in 0, and we see that we can get negative 6. If we plug in x equals 1, we get negative 1. It's not quite positive yet. If we plug in 2, though, I'm going to bet that f of 2 is positive. So maybe we can use the interval from 0 to 2, or maybe from 1 to 2. Let's choose a to equal 0, since it's pretty easy. And f of a, which is f of 0, is minus 6. And why don't we choose b to be 2? F of b, or f of 2, if we evaluate the function at 2, we get 16. So we know that 0 is a value between f of 0, which is less than 0, and f of 2, which is greater than 0. By the intermediate value theorem, since the function is continuous on 0 to 2, we must have a value between 0 and 2. We can call it c, where f of c equals 0. Now, this at least tells us that there is a solution to the equation. And that's not exactly what we're trying to achieve here. We want to show that this equation has exactly one solution. And that means that it cannot have 2 or more solutions. And so we're going to use Rolle's theorem in a slightly unique way to show that we can't have 2 solutions. Looking back at Rolle's theorem, we know that whenever f of a equals f of b, in this case, let's assume f of a and f of b both give 0. Meaning that there are 2 places where the function crosses the x-axis. Well, in that case, if we know that function is continuous and differentiable, there must exist a value where the derivative equals 0. What we're going to show is that this is impossible to have as a conclusion. If this is impossible to have as a conclusion, and we know that the function is continuous and differentiable, then this third criteria must be impossible to achieve. So let's see if we can do that. We first need to also state the other criteria. We've got continuous, but for mean value theorem, we need to say that our function is differentiable on an interval. But we have a function that is differentiable and continuous over the whole real number line. Now, let's assume that there is an a and a b, that both are places where the function crosses the x-axis. Let's assume that f of a and f of b are both equal to 0, with a not equal to b. In other words, this equation has two solutions. Well, by the conclusion of the mean value theorem, there must exist some sort of number c in between those two x-intercepts where the derivative of our function is equal to 0. Now remember that you can just draw a little picture here. We're assuming that our function crosses the x-axis twice, once at a and once at b. And if this is a continuous and differentiable function, if it crosses the x-axis, it's going to come back down and cross the x-axis again and have a horizontal tangent line. Or, of course, it could go and cross and come back up. It would have to, again, have a horizontal tangent line. But what is the derivative of our function? The derivative of our function is 6x squared plus 3. And this is always going to be greater than or equal to 3. So the derivative can't equal 0. That means no such value c may exist anywhere on the real number line. This means that we cannot have f of a equal f of b equal 0, with a and b being unique values. And as a result, we cannot have a second solution to the equation 2x cubed plus 3x minus 6 equals 0. And putting these pieces together, we know that we have at least one solution, and we cannot have two or more solutions. Therefore, our equation has exactly one solution. All right, so this kind of uses two theorems. It has the intermediate value theorem as the first part to show that something crosses the x-axis. One endpoint needs to be negative and one endpoint needs to be positive, and the function needs to be continuous. And then the second part, using Rolle's theorem, if it's differentiable, then if it were to cross the x-axis twice, the derivative would have to equal 0. If the derivative can never equal 0, it's impossible for our function to have that kind of behavior. It can't cross the x-axis twice. Going back up to Rolle's theorem, really just thinking about this dotted line being the x-axis, if you ever start and end at the x-axis and you're continuous and differentiable, somewhere in the middle, you're going to have a horizontal tangent line. And that was impossible in this last example. Now, where would we use the mean value theorem? Well, let's take a look at building a railway. Now, in Canada, the maximum grade for rail is 2.2%. And this is actually a weird way of measuring slope. Whenever we're measuring the slope of road or rail, we use grade, which is actually as a percentage. So really, this means that a slope would be 2.2 out of 100, where for every 100 meters of rail, the maximum change in elevation is 2.2. Now, if we wanted to have a section of rail 3,500 meters long, or 3.5 kilometers, what is the maximum change in elevation? Well, first of all, a rail line is a continuous function, and it's going to have a nice smooth surface, so it's also differentiable. We also have a total length of rail here of 3,500 meters. So why don't we say that the distance from A to B here is 3,500, or really just B minus A is equal to 3,500 meters. Now, the maximum change in elevation, that's going to be from our endpoints here. What is the maximum change in elevation f of b minus f of a? Well, by the mean value theorem, if we have a continuous and differentiable function like a rail line, then whatever f of b minus f of a is, it will tell us that at some point in time on the rail line, we have to have a derivative. F prime of c equals f of b minus f of a over b minus a. And because of a maximum grade of rail, we know that the slope at any point in time in this section of track, f prime of c has to be less than or equal to 0.022 or 2.2%. And if it is sloping downwards, the maximum slope downwards would be a negative 2.2% grade. So now that tells us that we can have these two equations put together and give a restriction on the total maximum change in elevation. By plugging this in, see that the slope of the secant line connecting the two endpoints must be between a negative and positive 2.2% grade. And b minus a here is 3,500 meters, so we can plug that in. And then we can multiply all three components of this inequality by 3,500. And that will cancel 3,500 from the middle. And this tells us that f of b minus f of a is any value between 77 and negative 77 meters. And so the maximum change in elevation over a 3,500 meter stretch of track is plus or minus 77 meters. And there are other uses for the mean value theorem. This isn't really the only one, but you can see this in planning out roadways and railways. If we need to have more than 77 meters of elevation change, that means we need to build a longer stretch of road to get there. And that's why we would have maybe a few different switchbacks in order to climb up to that sort of elevation. Or if you take a look at some rail lines, especially a very good example in BC, we actually just hollowed out a big tunnel throughout a mountain and increased the length of track so we could spiral it through the mountain and come back out. And that gave us enough distance to be able to climb up through some of the rocky mountains. You can take a look at that. It's called the spiral tunnel. All right, well, there are many other examples we could mention. Hopefully I'll be able to show you a few more in class, but we'll save the rest of that for future videos. Thank you for watching. I'll see you in the next video.